Hello students, this is a continuation of our previous lecture on Bessel equation. So we are finding the solutions of the Bessel equation of order 0. So now already we have found the first solution phi 1 of x. Now we are going to find the second solution phi 2 of x. From equation 1, what do we have phi 2 of x to be equal to? So phi 2 of x is equal to, so we had phi 2 of x to be equal to x sigma 2 of x plus log x phi 1 of x. Now what we are going to do, this x sigma 1 of sigma 2 of x is we know that sigma 2 has the power series expansion, and just multiplying this x with the power series expansion, we are going to take this x sigma 2 of x to be equal to summation k equal to 0 to infinity ck x to the power k, and so hence c naught will be equal to 0. We have already seen about all this, so I'm just refreshing it to you. So now in this x sigma 2 of x, we are going to take it as summation k equal to 0 to infinity ck x power k. So now what we shall do, we know that this phi 2 is a solution of L of y equal to x squared y double dash plus xy dash plus x squared y. So because phi 2 is a solution of this, L of phi 2 will be equal to 0. So from this, which it implies x squared phi 2 double dash plus x phi 2 dash plus x squared phi is equal to 0. Now what we shall do, we shall find this phi 2 double dash and then plus phi 2 dash and phi 2. We will find all this and we will substitute in this equation. Now from here, what is phi 2? Phi 2 can be written as this, that is, I have substituted x sigma 2 of x, this value, in phi 2 of x, and this is our phi 2 of x. Now from this, what will be phi 2 dash of x? So we need to differentiate this. So already I told you, while differentiating this, it will become k equal to 1 to infinity ck k multiplied with x to the power k plus, now this has to be done by using UV method. So when we use UV method, first we can have phi 1 as it is. So phi 1 of x multiplied with the differentiation of log x is 1 by x. So we can write this in this way, and then plus, now we will have log x as it is and differentiate phi 1 of x, and so we get log x multiplied with phi 1 dash of x. So this is what we obtain for phi 2 of x. Phi 2 dash of x. Now using this, we will find phi 2 double dash of x. So phi 2 double dash of x will be equal to, now differentiating this again, we get summation k equal to 2 to infinity ck k multiplied with, this should be k minus 1. Please make that correction, I didn't write here. So because after differentiation it will become k minus 1 here. So again differentiating k into k minus 1 x to the power k minus 2. Now we have to differentiate these two by using UV method. So that will become plus, now it will be x squared, so x multiplied with phi 1 dash of x minus phi 1 of x multiplied with 1 because the differentiation of x is 1 plus, now again we have to differentiate this by using UV method. So first we can have this as it is, that is phi 1 dash of x as it is, and differentiating log x we get 1 by x plus, now we will have log x as it is, and differentiating phi 1 dash of x we get phi 1 double dash of x. So now what we will do, we will simplify this. So this will be equal to summation k equal to 2 to infinity k into k minus 1 ck x to the power k minus 2. Now this term can be written by separating the denominators. So we will be having x phi 1 dash of x by x squared. So cancelling the x terms, we will have phi 1 dash of x by x minus, and so this will be phi 1 of x divided by x, and then x square. Okay, so this x phi 1 of x by x square, and then plus phi 1 dash of x by x plus log x, okay, and then phi 1 double dash of x. So all these terms comes as it is. Now after this we observe that these two terms are same. So we can write it twice. So what we obtain is, we obtain this, that is adding these two terms we can write it twice, phi 1 dash of x by x, and this negative phi 1 of x by x square I have written here, and then plus log x phi 1 double dash of x. So we have obtained phi 2 dash of x and phi 2 double dash of x. Now we have to substitute all this in our equation L of phi 2 of x equal to 0. So before substituting, here it should be k minus 2, okay, because we have k minus 2 here. So right here x to the power k minus 2. Now we will substitute all this in L of L of phi 2 of x equal to 0. So this is the equation. So now here phi 2 double dash of x we have to substitute. So multiply x square with phi 2 double dash. So what is phi 2 double dash we have obtained here? So this is phi 2 double dash of x. So if we multiply x squared with this term, so this term gets multiplied with x square, and so the power of x becomes k here, and that is what I have written here, k equal to 2 to infinity k multiplied with k minus 1 ck x power k. And then x squared when multiplied with this term, x squared and x squared gets cancelled, and so we have negative phi 1 of x. So that I have written here, negative phi 1 of x, plus now here when x squared is multiplied, one of the x gets cancelled, and in the numerator we will be having 2x phi 1 dash of x, and so that I have written here 2x phi 1 dash of x. And then x squared has to be multiplied with this term, so x squared log x phi 1 double dash of x I have written here. So this is that first full term, that is x squared phi 2 double dash of x fully I have written here. Then we have x phi 2 dash of x, that I have written here. So x has to be multiplied with phi 2 dash of x. What is phi 2 dash of x? Just now we have found here. So now this term has to be multiplied with x. So when we multiply x with this first term, the power of x becomes k. And with the second term, when we multiply x, x and x gets cancelled, and we have phi 1 of x alone. And here when we multiply x, we get x log x phi 1 dash of x, which I have written here and I have shown you. So this is the this second term, and then we have to multiply x squared with phi 2 of x. So what is phi 2 of x? Here we have, so with this we have to multiply x square. So when this term is multiplied with x square, the power of x becomes x power k plus 2 plus x squared log x phi 1 of x, which I have written here. So hope you understand this. Now we shall proceed further for simplification. So on simplifying this, what do we get is this negative phi 1 of x and positive phi 1 of x gets cancelled, and this summation terms remains as such. We will put all the summations together, but we notice that here we have summation k equal to 2 to infinity. Here we have summation k equal to 1 to infinity. So how shall we convert this for k equal to 2 to infinity? We will substitute k equal to 1 first. So when we substitute k equal to 1, this 1 multiplied with c1x, we will x power 1, which is c1x. So this full term can be written as, I will just show you here, c1x plus summation k equal to 2 to infinity k ck x power k. So this one term, okay, can be written like this, so that we can gather this term, and what is here, k equal to 0 to infinity. How to make it k equal to 2 to infinity? By replacing k by k minus 2. If you remember the previous video, we have done the same format. In the same way, if we replace k equal to k minus 2, this will turn out to be summation k equal to 2 to infinity c k minus 2 x to the power k. So now this term and this term can be combined, and it can be written as one summation. Okay, so we will write that now. So after combining, I obtain like this, that is, this term is c1 of x plus, or in everything summation k equal to 2 to infinity is common, and here we will be having k into k minus 1 plus k. So on simplifying this, we get k squared and then ck plus ck minus 2 x power k. So this is what we obtain. Now the remaining terms we will write. So this I will write here. plus the remaining term, if we see, we have 2x phi 1 dash of x in this term. So that we will take and write. So plus 2x phi 1 dash of x plus, now if you see in these three terms, so that is x squared log x phi 1 double dash of x, and then x log x phi 1 dash of x, x squared log x phi 1 of x, we observe that this log x is common in all these three terms. So we will take that log x common out, and within the bracket we will have in this term what is left out after taking log x, x squared phi 1 double dash of x we have. So that we will write. So x squared phi 1 double dash of x plus, now in this term we, after taking this log x common out, we will have x phi 1 dash of x. So that we will write. So x phi 1 dash of x plus, now in this term we have x squared phi 1 of x. So x squared phi 1 of x. So all together, that is this full term is equal to 0. Now in this we observe that this is nothing but L of phi 1. But what is L of phi 1? L of phi 1 is equal to 0. So this full term becomes 0, and when log x is multiplied with this term, this complete term vanishes and we will be left out with c1x plus summation k equal to 2 to infinity k squared ck plus ck minus 2, and this term, if I take it to the right, 2x phi 1 dash of x, it will become equal to negative 2x phi 1 dash of x. So this is what we obtain. Now in order to simplify this equation, we need phi 1 dash of x. From the previous lecture, we know that phi 1 of x is equal to this one. So this solution we obtained in our previous video. So from this, what will be phi 1 dash of x? It will be equal to summation m will turn out to be, the summation will be for m equal to 1 to infinity, because after differentiation it reduces by one term. So and then these are constants which will remain the same, and this when differentiated it will become 2m multiplied with x to the power 2m minus 1 divided by 2 to the power 2m and then m factorial the whole square. Now this quantity we have to substitute here. So let us do that. So here you write x bar k, which was missed in this equation, and now substituting phi 1 dash of x in this, we obtain this one. So I have substituted phi 1 dash of x on the right. So now this right hand side can be further simplified. So what we will do, we will take this negative sign within the bracket, and so it will be summation m equal to 1 to infinity negative 1 to the power, already we have m here, so it will be m plus 1. And after that, here we have x. When this x is multiplied with this x, it turns out to be x to the power 2m minus 1 plus 1. So it will get cancelled, and so we will have x to the power 2m. And we have an m here, which I will just multiply and write here, divided by, now this 2 and this 2 will become 2 squared. And when taken to the denominator, it will become 2 to the power 2m minus 2. So the 2 square which is in the numerator comes to the denominator as 2 power minus 2, and added up with this 2m we get this, and then factorial m the whole square. So this is our right hand side, and in the left we have these terms. Now comparing the coefficients on both the sides, we observe that the value of c1 is equals to 0. And since c1 is 0, this will imply that all the odd powers c3 will, which is equal to c5 equal to c7, will be equal to 0. So from this we see that only the even terms with even powers remains, because the right hand side is also all terms of with power x has the power 2m, which is an even term. So now since the right hand side is even, now we can put k equal to 2m, and so we're comparing the coefficients on both the sides of x power 2m. So this will become x power 2m, and here also we have x power 2m. So this and this, while comparing the coefficients on the left and right, on the left we have taken k equal to 2m, so this we will get it as 2m the whole square, okay, because we have k square. then ck. So c2m plus ck minus 2. So c2m minus 2 is equal to. So on the right here we have this term. So its coefficients is negative 1 power m plus 1 and then multiplied with m divided by 2 to the power 2m minus 2 and then factorial m the whole square. So we have obtained this recurrence relation. Now in this recurrence relation we will find when m is equal to 1. What happens? We get this becomes 2 squared and then when m is 1 this will be c2. Okay, plus c, and when m is 1, 2 minus 2 which is c naught is equal to, and again here negative 1 squared and m is 1 divided by 2 to the power 2 minus 2 0 and then factorial 1 the whole square. So what we obtain here, c naught is already what? It is equal to 0. Previously we have taken. And then what will be a c2 then? So c2 will be equal to, on the right, negative 1 squared becomes 1. So 1, and then this is also 2 plus 0 is 1. This is also 1 divided by this 2 squared comes here, and so the value of c2 will be equal to 1 by 2 square. Now we will find the other value, which is obtained by putting m is equal to 2 in this recurrence relation. So when we put m is equal to 2 in this recurrence relation, what do we get? 2 multiplied with 2 square, which will be 4 square. So 4 square and then c4, okay, plus c. Now here it is 2. So 2 times is 4. 4 minus 2 is 2. So plus c2 is equal to, now the value of m is 2, right? So negative 1 power 3 and then multiplied with 2 divided by 2 to the power, now here m is 2, so 4 minus 2 is 2, so 2 squared and then factorial 2 the whole square. So this is what we obtain. So now in this one of the 2 gets cancelled, and what is c2? c2 is 1 by 2 square. So if we substitute that here and when we take it to the right, what we get here is 4 square c4 is equal to, the c2 when we take it to the right it becomes negative c2, so which is negative 1 by 2 square. So this term, and then here we have negative 1 cube, so it becomes negative 1 divided by, now in the denominator we have 1 2 here and then factorial 2 square. But what is factorial 2? Factorial 2 is 2 only, so it will be 2 square. And we observe that this 4 square, taking it to the right we get, and before that this also we will simplify. We will take the negative sign outside, and also we can take 1 by 2 squared outside, so that in the bracket we get, so here it will be 1 plus 1 by 2. So bringing that 4 square to the right, we get the value of c4 to be equal to negative 1 by 2 squared multiplied with 4 square, and within the bracket 1 plus 1 by 2. So this is what we get. In a similar way, we can find c6, which I will give it to you as an assignment. You just try it out, and what we obtain for c6 is, this is what we obtain as c6, and by the method of induction we can generally show that c2m is equal to, so this is what we obtain c2m as. So after obtaining this, we can substitute the c2m in the solution phi 2, and then the solution phi 2 will turn out to be, so the solution phi 2 of x is this. So on substituting c2m over here, we get this to be equal to m equal to 1 to infinity. c2m is this value. So negative 1 power, I'm going to take m alone here because I'm going to have a negative sign outside. So that m plus 1 can be written as negative 1 power m because I'm taking a negative sign here, and then divided by this factorial m the whole squared I have written, and then this series, that is 1 plus 1 by 2 plus etc. up to 1 by m multiplied with, we have this x power 2m, and in the denominator here we have 2 power 2m, which can be combined and can be written as x by 2 the whole power 2m, and then here we have plus log x multiplied with phi 1 of x. So phi 1 of x can be written as j naught of x, which we obtained in the previous lecture. So j naught of x, and this phi 2 of x is denoted by k naught of x. So k naught of x is equal to this. This is what we obtained. Thus the solution determined is called the Bessel function of zero order of the second kind, and which is denoted by k naught of x. Thus, the above solution is known as the Bessel function of zero order of the second kind, which may appear in 1 marks also. You can just make a note of this solution. So, thus with this video we complete the total solutions of Bessel function when alpha is equals to 0. So, we have found phi 1 in our previous lecture, and in this lecture we have found phi 2. So, combining these two solutions, we get the complete solution of the Bessel equation. So, hope you have understood both the lectures. Thank you.